This is Jack Jackson again. In this video, we're going to be looking at limits as x goes to a constant, but the limit is infinity or minus infinity, at least from one side. And these are situations where we end up having a vertical asymptote. So there's a formal way we can define this, and we're going to investigate this with an app that I wrote in GeoGebra. It's available on the GeoGebra's website, geogebra.org. And if you're in my class, I'll give you a direct link to this particular one. Okay, so the way this app works is you type in a formula for a function in this box here. Right now I'm using f of x equals 4 divided by x, and a x value that you're approaching, a c of, in this case, 0. So x is approaching 0. We want to see what the limit of 4 over x is as x approaches 0. Now, it doesn't have a limit. In fact, if you can see what happens is from the right side, it goes up forever. So the limit from the right is infinity. Limit from the left is negative infinity. That doesn't really say that it exists. It just explains how and why it doesn't exist. We can make that formal with the following definition. It shouldn't have this horizontal line here. We say that a function has a vertical asymptote from the right, and the limit as x approaches c from the right, that plus means, of f of x equals infinity, which is a way that it does not exist, if and only if for every m greater than 0, there exists a delta greater than 0, such that if x is greater than c, but less than x plus delta, then f of x is greater than m. So the way this works here in the app is the way you can see this is if we pick an m, and it can be any value we want. At this point we're looking only at the top part of this graph, not the bottom part. Okay, but let's say we put it at 6 here, which we can also get by just typing this in. Maybe we put it even smaller, so we put it at 4. You can type in a number there, or you can do it with the slider. That determines this line y equals m. Ignore down here for the moment. Now, what we're saying here is if we pick delta small enough, that any x's that we pick in here will end up giving us y's that are above that value of m. In other words, the graph is above this line between c and c plus delta. In other words, between 0 and 1 in this case. And so if we pick x's in here, that's what this little dot can do. It can only pick x's in there. Look where the y's end up. They always end up below that line. The lowest is right there. It's okay for it to be at a corner, but it's either at a corner or going up higher. It's not going out the bottom of the box. Okay? Whereas if we had, let's say, a little higher m, that delta would not be small enough because there are some deltas, like some x's that are in there that the graph is too low. See, it's not high enough. What we're doing is we're saying the graph gets higher and higher and higher and higher. And so the idea is however high we put it, we just pick a smaller delta, and now all of the x's in here produce y's that are above that line. When you say, well, let's do a smaller or larger, say, well, let's say, okay, no, you got to be bigger than a higher value. I may have to zoom out to see it here. But there's some place in there that if I pick the delta small enough, we're not there yet, but if I pick the delta small enough, then all of the values will be above that. So hopefully, and the idea is no matter how high we put m, that we can go small enough with delta. If we're within that, all the values above that. So that says the limit as you go from the right of this function goes to infinity. Now, it goes to negative infinity as we come in from the other side. So what you do is you leave this the same. You pick I'm going to do it this way, where we pick an m greater than 0. The only difference is f of x has to be less than minus m. That doesn't fit the definition of an actual limit existing, but it's a way that the limit might fail to exist. And that gives us a vertical asymptote from the left. So down here is the graph of line y equals minus m. So we can use the exact same graph and so forth, to work with it. But this time we look at this point here for what's happening on the left, and we see that all the y's are down here below that horizontal line. In fact, we could have gotten better by with a bigger delta, probably right about there where these two cross. And so from there on out, any x's that we pick here will give us y's that are below that line y equals minus m. And so that's formally how we define what's meant by a vertical asymptote, or these one-sided limits going to infinity or minus infinity. Now, if you don't have the plus or minus there, this one has the minus, you plus. If you put the minus, you'd be coming from the left side. That would be looking at the green rectangle, or the pink one if it's going to positive infinity. In this case, we would definitely say the limit as you're coming from both sides does not exist. And not only that, we couldn't say it's infinity or minus infinity, because one side on the right goes up towards positive infinity, whereas on the left it goes down to negative infinity. If they were both going up to positive infinity, like say 4 over x squared, for example, then here both the left and the right limits are approaching infinity as x goes to 0. So you would say the limit as x goes to 0 of this function equals infinity. But once again, don't confuse that with saying that the limit actually exists. It's just describing how and why it does not exist. So hopefully this applet will give you something you can experiment with. You can type in your own functions there, experiment with different values of c and m and delta, and explore this on your own. As you go down below, you'll also see some formal definitions and directions. Perhaps even some questions down here sometimes on these things. Okay, hope you enjoy that.